All right, today we're going to talk about solving quadratic equations by finding square roots. So the essential question is, how do the properties of square roots help us to solve quadratics? Here we have some properties of square roots. You always have to be talking about a positive number underneath the symbol is called the radical. So you always have to have positive numbers underneath the radical for now. And we have the first property called the product property, where if we multiply two terms together, we could also separate into the square root of a times the square root of b. We have another property, the quotient property, that says if we're dividing underneath a radical, we could separate that into the square root of a divided by the square root of b, rather than just square root of ab or square root of a over b. Here's a helpful list. It's the square roots of 0 through 15, or the perfect squares 0 through 15. So you should pause the video and write this down if any of these were, I don't know, surprising, or you just need to refresh a little bit. But the trick is, when you're simplifying radicals, you need to factor the number underneath the radical and look for the perfect square factors. Here's a short list. We have 1 and 27, and we have 3 and 9. Look for the biggest perfect square you can find. I see 1, I see 9. So we're going to go with the pair 3 and 9. Perfect squares to the front, leftovers to the back, but you're going to rewrite 27 as a product. Oops, not 3, 2. Or not 2, 3. And then, according to the product property, we can break it apart into the square root of 9 times the square root of 3, which is 3 square root 3. Then for 98, factor and again, you want to look for the biggest perfect square that you can find. So for us, 49 is the biggest perfect square we can find. So we're going to rewrite the square root of 98 as the square root of 49 times 2. Perfect square to the front, leftovers to the back, and we're left with 7 square root 2. If we're multiplying two radicals together, we're going to take one extra step and put it underneath one radical symbol. So 10 times 15 is what we're looking for the square root of. So 150. Then we can factor out the number 150. And then again, we want to look for the biggest perfect square factor. So I see the number 1 is a perfect square. If I keep going, 2, 3, 5, okay, I see 25. And I don't see any other perfect squares. So it looks like our biggest perfect square factor is 25. So we're going to rewrite the square root of 150 as the square root of 25 times 6. Break the radical into two radicals, and we should have 5 square root 6. All right, let's talk about division. So right now we have a square root. We have a radical, I should say, with a fraction underneath. So we can break that apart into two separate square roots, which is square root of 9, or square root of 9 divided by square root of 64. And then you can just simplify. Square root of 9 is 3. Square root of 64 is 8. And we're done. Next we have square root of 15 over 4. Break it apart. The square root of 15 is fully simplified. We can't break it apart anymore. But the square root of 4 can become 2. And there's our answer. We have a rule that tells us that we are not allowed to have radicals in the denominator. So if that does happen, it's the same first step still. Break it apart, square root of 3 over square root of 5. But then to make a square root go away, you have to square it or multiply it by itself. So we're going to multiply both the numerator and denominator by the square root of 5. And you can put this underneath one single radical. If you see the shortcut after a while, you can just get rid of the square root symbol and write the 5, but because it helps to see all the steps out, first I'm going to show you exactly what to do step by step. The square root of 5 times 5 is the same as square root of 25. And this becomes square root of 15. Like we said on the last slide, 15 is already as simplified as it gets over 5. And then we're done. And we can try the same thing for the next example. Break it apart. Neither 7 or 11 have any perfect square factors, which doesn't really matter about the 7, but for the 11, we need to multiply. We need to multiply the square root of 11 by the square root of 11, but because it's a fraction, we have to multiply both the numerator and denominator by the square root of 11. Seven times 11 is 77. 11 times 11 is 121. And then we're left with the square root of 77 over the square root of 11. Sometimes we can simplify the denominator just a little bit. This example here is one case where we can. The square root of 12 will not be a perfect square factor, but we can factor out the number 12. And look for the biggest perfect square factor, which is 4. And then the square root of 4 simplifies to 2. And we can simplify this just a little bit. If we do 10 divided by 2, we get 5. And 2 divided by 2 becomes 1. So this becomes 5 over the square root of 3. And now we just have to multiply the numerator and denominator by the square root of 3. So because the 3 is underneath the square root and the 5 is not, we cannot do the square root of 15. It has to be 5 times square root of 3. And then for square root of 3 times square root of 3, that becomes square root of 9. And this whole expression simplifies to 5 square root 3 over 3. Okay. Sometimes we're going to have some expressions where it's not as, it takes a little bit more because we're not just multiplying a square root. We're not just simplifying a square root. We'll have something where we're adding a square root or we're subtracting a square root, like these two examples. So before we can simplify something like that, we have to talk about this idea of conjugate. Anytime you are adding a rational or an integer and a square root together, its conjugate is the pair where you have that same integer but you are subtracting the square root. The product always becomes a rational number. So I know right now I'm just saying integer, square root. Let's look at an example. For that first slide I looked at, it was 4 over 5 minus the square root of 2. So that follows this form here. So we have to multiply it by what's called its conjugate, which is going to be 5 plus the square root of 2. So I'm going to put the entire denominator in parentheses. And I'm going to multiply it by 5 plus the square root of 2. But then because I did that to the numerator, I'm also going to have to do that to the denominator. And then why does that work? This is just like when we multiply out binomial terms. You can use the box method. Fill in each box, and then 5 times the negative square root of 2 is going to become negative 5 square root of 2. We can't simplify a rational number and an irrational number. And then when we multiply the negative square root of 2 times the positive square root of 2, it's going to be negative square root of, because these two are both underneath the square root, we can write 2 times 2. So if I were to write this all out, it would become 25 minus 5 square root 2 plus 5 square root 2, and then minus the square root of 2 times 2 is 4. So because we have a negative 5 square root 2 and a positive 5 square root 2, those are going to cancel. This becomes 25 minus 2, which is 23. So coming back up to the question, we have 4 times 5 plus square root of 2 over 23. We can't simplify that anymore. 4 and 23 are prime to each other. So we can distribute the 4. And this becomes 20. 4 times 5 is 20. 4 square root 2 over 23. We'll look at one more example. Because we have 9 plus the square root of 7 in the denominator, we're going to have to multiply by the conjugate again, which is going to be the exact same, but the addition will turn to subtraction. You're going to multiply out the denominator again. I filled it in because I'm running low on time, but then multiply each box, and I'm going to hit pause again for that. Then we're going to add up all of our terms. And then there again, we're going to have our middle terms cancel with 63 minus 7. After we come back to our original radical, we have 4 times 9 minus the square root of 7 over 56. 4 and 56 can be reduced to 1 and 14. So we're left with 1 times 9 minus square root of 7 over